Hello again, this is Ty Warner with KISSsoft, a division of Gleason Corporation, and I want to talk today about force response on shaft systems. So what we can do in KISSsoft, and this is in our shaft module, is we can design a shaft. You can see I've got a shaft here, I've got a coupler, I got a gear, and then I have this mass out here that's spinning. So what I do is I create a shaft, and I put some forces on it. In this case, I'm calling this a propeller or a fan. In this mass in particular, we can add some specific data in the moments of inertia around the X and the Z axis, and as well around the Y axis, which would be polar moment, J. So we also add the mass of this overhung load, and then here's the big thing, is we can add this eccentricity right here, and we can make this whatever it is. You can actually look at it in terms of an unbalanced spec, depending on how fast this shaft is spinning. Your basic data, I want to put this at 1400 for now. I can consider the gyroscopic effects and weight. I'm going to do this gears mounted by interference to fit with stiffness. I'm going to calculate 4 eigen frequencies, and I am going to try and look at the inner bearing geometry for stiffness. The housing material, we'll just say it's a steel housing, and then the lubricant's an ISO VG220, and we're going to set the rolling life bearing to 2,000 hours right here for the rolling bearing life. And we're going to now, because we've specified these bearings, I've even given a little bit of preload for the design. 0 on this side and a little bit on this side. This gear happens to be a helical gear, so I've got a little bit of preload to handle that axial force. And you can see I have a couple other things that I've added here. You see these look like our cross sections, but they're not actually cross sections. They're documentation points. So we want to put the documentation points on our bearings right here and right here, kind of in the center of our bearings. Well, this documentation point is what we need when we look at a force response for the shaft. If I go in here to my shaft and I say I'm going to spin this at 2,000 RPMs, I'm going to get a warning. I know I'm going to get a warning. It's going to tell me that I might have exceeded my thermally safe operating speed. So when you get these types, you can see we have lots of life right here. You can see our loading for the bearings. You can see our critical speeds. I'm going to open this thermally safe operating speed for these bearings. Now these are bearings that I just pulled out of our bearing database. And I'm going to say, yeah, it's to the middle of the lowest rolling body, so we could do the middle of the bearing. Bearing oil and mist, we could do that. I'm just going to go to the lowest roller bearing. I'm not going to change the temperature. I'm going to calculate. When I calculate this, it tells me that I'm going to be in excess of my safe operating temperatures. And it tells me what I can have, 1400 or 1575 roughly. So what I've done is I went back to my basic data and I changed this to 1400. And I run this again, and now I'm not getting that error or that warning. I changed this limit to limited life strength here as well to 2,000 hours. But now I want to see what my force response is for my system. So I've got this imbalanced mass right here. It's just a right click, add magnetic additional mass. So think of this like a big fan out here that's unbalanced, right? And what we want to do is we want to look at what that unbalanced force causes for forces back here on my bearing positions. And that's why I put my documentation points on my bearings, because I'm interested to see what those are going to see under high load. So I go to force response. I set my speed limits. I set the 60,000 high because I want to make sure I can capture it. And I grab shaft 1. And I'm going to look at the reference speed. So there's some material damping information you can change. This is pretty standard for steel. So now I go ahead and I run my forced response. It takes a moment to calculate. And I have, it gives me the maximum value of large half-axis of the trajectory and corresponding speed. So it does depend on damping values. However, you see shaft 1 here, this is my documentation point for my left-hand bearing and my right-hand bearing. And it tells me the large half-axis of the trajectory. So what it's telling me is a normalized displacement at resonance from that force, that imbalance force, is at 12,000 RPM, 12,324 RPMs, is 6.5 millimeters. Now, that's also taking into account, I think, the housing deflections as well. So, we go to graphics, grab shaft, we can look at the displacement. This is the typical displacement of our shaft with that load. And, you know, it's not much, it's pretty small. But then when we look at the graphics, shaft, forced vibrations, we can get a better idea of what our bearing loads are going to be if we run this thing at resonance. So my speed from 100 to 60,000, this is my major displacement of orbit, this is my whirl, right? Now if I want to look at the X component of this, because right now we're looking at the major semi-axis in the Z, I can turn this over to X, Y. So this is a normalized displacement, right? So this is what the normalized displacement would be at roughly 12,000 RPM. And this is at my left-hand bearing right here. Now I can change this to my right-hand bearing, and you can see there's a difference there. It's even higher. We would expect it to be higher because that's where we would think the largest load would be. Now, so that's my displacement at this RPM, or this speed range right here. But maybe I'm interested in the force at that bearing location. So here's the force response then of the bearing at these loads just from the imbalanced masses. Okay? 450 pound force, and this is in the Z direction. We can plot it in the X direction. You can see it even goes higher. It's pretty low here. So it's at some, if you coupled those two forces, you'd get an angle offset, and you'd know what direction plane that is in. And we also have some Y excitation amplitude, right? So at this frequency range right here, which is 12,324, and then another one at 28, you have some axial force response, and these are those loads. There's other things you can pull out of here for information. You can pull out the torque. Look at the X and the Z components of the torque. You can also look at rotation if that's something that you're interested in. So that might be some torsion stuff. You can also look at the minor semi-axis of orbit, whirl. So this is some information that you can pull out of here and use. Sometimes you might be more interested in, instead of speed, and you want hertz, right? So here'd be your hertz. If you change this over here, you can always change some of these things. You can always add your legend in here. I think this force one is a pretty interesting one. So you can look at it in terms of frequency. And you can turn the legend on. So this is the forced response. Make sure when you're working with this, you're putting your imbalanced mass out here for your calculation. And you can see here in your displacement, this mass is being taken into account. So this guy here weighs, oh, what does it weigh? 48 pounds in this particular example. I have a coupler on the back side, so I'm basically saying that I'm driving maybe into this shaft and driving in something else off of this gear, and I'm also driving a fan out here as an example. But make sure you get your documentation points in. Make sure you check your thermally safe operating speed of your bearings depending on how you're set up. And good luck with your forced response calculations. Very powerful tool. If you have questions, you can contact me at ty.warner@KISSsoft.com. You can also go to our webpage, www.KISSsoft.com. It's KISSsoft with 3 S's. You can also go to the webpage and ask for a test license if you're interested in one. But this is a forced response. If you have questions, go ahead and call me, get a hold of us, call our support team, and we can support you there very well. Thanks for watching.